In this video, we solve problem 14.5.019 from the Larson and Edwards Calculus Early Transcendental Functions text, 7th edition. We're asked to find the area of the surface, and the surface is the portion of the sphere given by x squared plus y squared plus z squared equals 400. Inside the cylinder, x squared plus y squared equals 144. Now with this problem and any similar problem, I would start by sketching. Let's sketch that surface. First, we have a sphere. X squared plus y squared plus z squared equals 400. Now, since we're not subtracting anything from the x, y, or z here, we know our sphere is centered at the origin, 0, 0, 0. And comparing this to the standard form of the equation of a sphere, this right-hand side is our radius squared. So we know that the radius squared is 400, which means that r is the square root of 400, or 20. So we've got a circle of radius 20 centered at the origin. I don't know if I said that correctly. A sphere of radius 20 centered at the origin. I think I may have just said circle. All right. So that's what we've got. Now we don't want the area of the whole sphere. We just want the area of the portion of the sphere inside the cylinder given by this equation. Now, if you see that equation and you're thinking of a circle, that's a very good thing because in the XY plane where z equals 0, this is just a circle. Not really happy with that circle, but that's okay. It's been through a lot. Since we're not subtracting anything from the x or the y, this is a circle centered at the origin. And the radius squared is 144, that right-hand side. Take the square root of 144. That gives you the radius of that circle. So this is a circle of radius 12 centered at the origin. But since we're in Calc 3, it's not just a circle of radius 12. X squared plus y squared has to be 144, but it's a cylinder. Z is free to be anything. Since Z is free to be anything, we have this circle in the XY plane. Try to draw it like that. And we're going to see the same circle when z equals 1 and z equals 2 and z equals 3 and z equals 20. It would just keep going. So that cylinder will intersect the sphere at the bottom and at the top. And what we want is the area of that portion of the sphere inside that circle or inside that cylinder of radius 12. So it's like a little cap of that sphere, and we're going to have a cap at the bottom as well. Okay, so that's the surface that we're looking for the area of. So now that we have a visualization of that surface, let's set up our surface area integral. We derived this formula in class. The surface area is the double integral over the region R of the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. And we're integrating over the region R, where R is the projection of our surface onto the XY plane. So I'm looking at the projection of the surface onto the XY plane. And when I say projection, what I mean is if the sun was up here and the sun was casting a shadow on my surface like this. The question is, what would that shadow look like? Well, that shadow would look like that. We want the x and the y that are associated with z values on our surface. That's a projection. So that circle of radius 12 centered at the origin in the xy plane, that is our region R. And z is the function of two variables, x and y, that describes that surface and that surface. Now, since we've got two parts to this, and since we're dealing with a sphere, so that the area of this part is equal to the area of this part, what I recommend is just computing the area of this part and doubling it. So we will compute this, but then we'll multiply by 2. We'll compute this for that top part of this sphere, that spherical cap, and then we'll double it to find both pieces. Okay, so in order to use this formula, now I need an equation for z in terms of x and y when we're on that sphere. Well, we already know what z is in terms of x and y. We know that x squared plus y squared plus z squared equals 400. So I can just take this equation and solve for z. So we'll subtract x squared and y squared from both sides. We'll take the square root, and then we'll just focus on that positive square root, because I just want the part of my sphere where z is positive. I want that top part. We're going to use this for our z to find the area of that top part, and then we'll double it to find the area of the top part and the bottom part. Now we're about to differentiate, to take partial derivatives with respect to x and y. So it would help to write that square root as a 1/2 power. That's where we're at. Okay. So we have z equals, open parentheses, 400 minus x squared minus y squared to the 1/2 power. And we want the partial derivatives of z with respect to x and y so that we can substitute them here and then set up and then evaluate that surface area integral. So we can notate that this way, or you can use Leibniz notation if you prefer. On the partial derivative of z with respect to x, that means we're differentiating with respect to x and treating y as a constant. Now, when I look at this, what I see is a function raised to the 1/2 power. So I've got an inside function raised to the 1/2 power. That means I have to use the chain rule from Calculus 1. Anytime you have a function nested inside another function, you have to use the chain rule. So I'll bring the power down. We'll multiply by the inside function to the 1 less power. That's the derivative of the outside. Always compute the derivative of the outside first. And then you multiply, or well, let me say it again. You take the derivative of the outside first. So we have 1/2 of the function raised to the negative 1/2 power. Put the inside function back inside. Don't change it. Then take the derivative of the inside and multiply by that. The derivative of the inside with respect to x, treating y as a constant, is just negative 2x. And the 1/2 and the 2 reduce. We end up with a negative x over the square root of 400 minus x squared minus y squared. Now, I want you to notice the symmetry with this function. If you switch x and y, you get exactly the same function. And that makes sense when we look at the geometry too. This is completely symmetric. Switching out the x and y is not going to change it. It's still a sphere. We still have that symmetry. So given that, I already know what the partial derivative of z is with respect to y. It's going to be exactly like this, but everywhere I see an x, I could replace it with a y, and everywhere I see a y, I could replace it with an x. So by symmetry, this partial derivative is negative y over the square root of 400 minus x squared minus y squared. Now, if you don't like that symmetry argument, if you're saying, I'm not sure that that's true, you could go ahead and compute the partial derivative with respect to y of this, and you would see that you get 1/2 times the inside function to the negative 1/2, and then the derivative of the inside with respect to y, treating x as a constant, is a negative 2y instead of a negative 2x, and you end up in the same place. You end up with exactly the same function here using the rules as you would by just switching x and y and getting this. So you can always confirm that for yourself if you want to. All right, so we've got our two partial derivatives. That is enough for us to set up the integrand here. for my surface area piece, I've got the square root of 1 plus the partial derivative of z with respect to x squared plus the partial derivative of z with respect to y squared. And I'll substitute those in. Now you've got a fraction squared for both of these. So you'll want to square the numerator. And square the denominator. Squaring that square root just gets rid of the square root. Negative y times negative y is positive y squared. And now we're here. Now these have the same denominator, so we can just add the numerators, keep that common denominator. And we'd like to get a common denominator for the entire expression under the radical. So I would write this one as 400 minus x squared minus y squared over itself so that it has the same denominator as these two expressions. I know you guys are in Calculus 3, so you probably didn't need that little reminder. That's okay. Sometimes we need reminders. And sometimes it's just comforting to hear that exactly what we think we're supposed to do is what we're supposed to do. Since these have the same denominator, keep that common denominator, add the numerators, write that 1 as that over that. And now these have the same denominator, and that means we can just add the numerators and keep the common denominator. Now, when I add the numerators, I have a negative x squared and an x squared, those cancel. A negative y squared and a y squared, those cancel. And so we just end up with this 400 over 400 minus x squared minus y squared. Remember from algebra, if you have the square root of a fraction, you can just take the square root of the numerator and the square root of the denominator separately. That's legal. So we'll take the square root of that numerator, which will give us a 20. And the square root of the denominator is just that square root of 400 minus x squared minus y squared. But that does not simplify. That is not 20 minus x minus y. You have to do the subtraction first and then take the square root. Okay, so that is our surface area integral in rectangular coordinates. But I notice a couple of things. I've got an x squared minus y squared under that radical. So I'm thinking I probably don't want to integrate in rectangular coordinates because that would require trig substitution, either in terms of x or y. I probably also don't want to integrate in rectangular coordinates because we're integrating over this region R. It's a circle or a circular disk of radius 12 in the xy plane. If I've got a circular disk, that tells me I probably want to switch to polar. Now remember, anytime your region is a circular disk or some part of a circular disk, or your integrand has some symmetry about an axis, and that's usually indicated by quantities that look like x squared plus y squared, then we probably want to switch to polar coordinates. And notice if we factor out the negative from this term and this term, we've got an x squared plus y squared right there. So this integrand would be easier to describe in polar coordinates because it has the x squared plus y squared in it, which means that the function itself has some symmetry about the what we would typically call the z-axis. And then the region of integration is a circle. So we'll do this in polar coordinates. That means we need three things to switch to polar coordinates. You need bounds in polar coordinates. We also need an integrand in polar coordinates. And we need a dA in polar coordinates. Now I'll just substitute dA here. Now dA used to be dx times dy. Now it turns out that if you switch to polar coordinates, dA is equal to r times dr d theta. And of course you could change the order if you wanted to, But we derived that when we came up with that area piece and we studied polar coordinates. Derived that in class, and there's also the derivation of that in the videos for polar coordinates on the Calculus 3 playlist. So we've got our dA that used to be dx dy. We're going to replace that with r d theta. Now we also need this integrand written in polar coordinates. So our original integrand was 20 over the square root of 400 minus the quantity x squared plus y squared. X squared plus y squared is just r squared. So we have 20 over the square root of 400 minus r squared in that case. And then our region of integration was that circular disk of radius 12 centered at the origin. Actually, we had that in blue before. So we need to describe that in polar coordinates. Now theta, we can think of as an angle that sweeps around the XY plane. It starts from one value and goes to another value. There are lots of different ways to express the range of values for theta here, but we only want to go around the circle once. I'm going to start at the positive x-axis and go back to the positive x-axis, and I'll use that traditional representation of that angle. We'll say theta starts at 0 and ends at 2 pi. Of course, you could go from negative pi to pi if you wanted to, or 0 to negative 2 pi. There are lots of different ways you could describe that range, but we'll just use 0 to 2 pi. Now for r, remember if r equals a constant, that means we're dealing with a circle of radius, absolute value of r, centered at the origin. So r equals 12 is the circle of radius 12. R equals 0 is just the origin. R equals 1 is a circle of radius 1. So as r goes out from 0 to 12, r is taking on all of those values. So I'm thinking of circles radiating out from the origin. 0 is, r equals 0 is just a single point, and then it goes all the way out to 12. So we have 0 to 12 here. Now, if you're saying, well, but is it always 0 to 12? It would still be 0 to 12 if we were just dealing with that little quarter of a circle in the first quadrant. But the fact that theta goes from 0 to 2 pi takes care of the fact that it's the whole circle. Or the whole circular disk. So that 0 to 12 says we've got circles radiating out, and then we go all the way around to get the whole thing. Okay, so we've got our bounds, we've got our new integrand, or our original integrand in polar coordinates, and then we've got our dA in polar coordinates. All you do is substitute. And remember, we're doubling it because we're finding the area of that top part of the sphere, and we'll double it to get the area of the bottom part of the sphere as well. So first we'll add the bounds. R goes from 0 to 12 when theta goes from 0 to 2 pi. This integrand is 20 over the square root of 400 minus r squared. And dA is r times dr d theta. With the new integrand, the new dA, and the new bounds, this integral is written entirely in terms of polar coordinates. And this is much easier to evaluate than this would have been in rectangular coordinates. Now remember, if we were describing this circle in rectangular coordinates, we'd have to have y going from the square root, from the negative square root of 144 minus x squared to the positive square root of 144 minus x squared. All of that would be true. You would have that here, and x would go from negative 12 to 12. Instead of having those ugly bounds and having to do trig substitution here, we can just do this. R is going to go from a constant to a constant, so is theta. And this integral is evaluated pretty easily. Now it is a quotient, so we don't have a rule for that. And we've got this expression under a radical, but we do have, if basic rules don't apply, since basic rules don't apply, we could try u-substitution, and u-substitution turns out to work. So it's nice and simple, nice and easy, something we're very comfortable with. Just jump right in with u-substitution here. Use u-substitution to evaluate the innermost integral, and then just sort of work our way out until we find the surface area. So I see a function nested inside another function. If I'm trying u-substitution, I'll assume that u is my inside function. Then we'll compute the derivative of that. The derivative of this with respect to r is just negative 2r times dr. That would give us our du. Now, I'm never really sure that u-substitution will work until I compute that derivative either in my head or on paper. And then I look at this and see if it's up here as a factor. And I say to myself, I can always adjust the constant. Do I have an r dr as part of my integrand? If I do, I can write this integral entirely in terms of u. And I do, I've got an r dr right there. So the u-substitution is going to work just fine. Everything here can be written in terms of u. So let's do it. Now, you have some options. You could take this equation and solve for r dr. In order to get rid of that -2, you could divide both sides by -2 or multiply by -1/2, same thing. Either way, it's up to you. Or you can say, I really want that to be a 20r dr because I've got a 20r dr right there. If I want this to be a 20r dr, I'd need to multiply both sides of this equation by -10. Of course, we're doing that because whatever we do to the left-hand side, we've got to do to the right-hand side. -10 times -2 is going to be that positive 20 that we wanted. So you have -10 du equals 20r dr. So this 20r dr can be replaced by -10 du. And I still have 2 times the integral from 0 to 2 pi on the outside. I'm not worried about that. 20r dr is the same as -10 du, so we can substitute that. I'll factor my du off to the far right. Now in the denominator, I've got 400 minus r squared. That's our u, but we're taking the square root of it. Don't forget that square root. Now, in order to convert this integral in terms of r into this integral in terms of u, I also need new bounds because remember, these are r values. This says r starts at 0 and ends at 12. If I've got an integral in terms of u, I need to know where u starts and where u stops. To find the bounds for u, we just substitute the bounds for r into this equation. So if we substitute r equals 12 here, get 400 minus 144, which turns out to be 256. We substitute r equals 0, we get 400. So our upper bound was 12. When we're at r equals 12, u is 256. So that's our new upper bound. Our lower bound used to be 0. When r equals 0, u is 400. That was a lower bound. This also is our lower bound. It's a lower bound because the lower bound goes with that lower bound. The upper bound goes with that upper bound. Now, a lot of students look at this and they're uncomfortable with it. They want you to go from the smaller number to the larger number, not the larger number to the smaller number. I get that. You can switch that. That's okay, as long as you multiply the integrand by -1. We talked about that in Calculus 1 a little bit. So we'll switch it. It makes everybody feel better. And then this -10 over the square root of u, we could write as a positive 10 over the square root of u. But I'm preparing to anti-differentiate. So I'm going to write this u, the square root of u, as u to the 1/2 power in the denominator, but then I bring it up to the numerator. So when I bring it up to the numerator, I'll have u to the -1/2 power. Just as a reminder, this comes from this. The nth root of x to the m is x to the m over n. The index of that radical goes in the denominator. So there's an implied 2 there that goes in the denominator. The 1 goes in the numerator. And then if I have something in the denominator, I can bring it up to the numerator as long as I change that sign. So I had a u to the 1/2 in the denominator. Now it's a u to the -1/2 in the numerator. Start on the inside, work your way out. And if you want, you could factor out that 10. 2 times that 10 is going to give us a 20. And now I'm ready to anti-differentiate. Just use the power rule, bring our u down, add 1 to the exponent. -1/2 plus 1 is +1/2. Then you want to divide by the new exponent. Dividing by 1/2 is the same as multiplying by the reciprocal, 2/1, or just 2. Now you want to evaluate this from u equals 256 to u equals 400. Because we changed those bounds, we never have to go back to r. You just plug in the u values and subtract, and you're done. 2 times 20 is going to give me a 40. And a u to the 1/2 is the same as the square root of u. So this turns out to be, when we evaluate at 400, square root of 400, then we want to evaluate this at 256. So I have square root of 256. And again, that 2 times that 20 gave me that 40. Those are all constants, so I'll factor those out of my integral. Now I just have the integral from 0 to 2 pi of d theta, or 1 d theta if you prefer. And this is 20. And this is 16. So I've got 40 times 4, which is 160. And we are evaluating this integral of 1 with respect to theta. So we just get theta. And we evaluate from theta equals 0 to theta equals 2 pi. So we get 160 times 2 pi minus 0, or 320 pi. And this was surface area, guys. So that's units squared. And if you're saying to yourself, what kind of units? Well, the same units that the x and y variables are measured in. That's the kind of units that we're dealing with here. So 320 pi units squared that's the area of this piece plus this piece. So I guess this is 160 pi units squared, and that's 160 pi to get us the 320. So I think that's it. Please let me know if you have any questions. Be happy to help you with this or other problems.